Good morning, everyone. Let's start. So I'm Cheng from Microsoft Research. I will chair this session today. So today it's our great honor to have Emtiyaz to give us a tutorial on the topic of deep learning with Bayesian principles. So Emtiyaz is a team leader at the Riken Center for Advanced Intelligence project in Tokyo. Actually, he leads a proximate Bayesian inference team. So he's also a visiting professor at Tokyo University of Agriculture and Technology. Previously, he was a postdoc in EPFL, where he actually won a Best Teaching Award. So looking forward for his tutorial.
Thank you for the great introduction. I would also like to thank the organizer for giving me this opportunity to be able to speak with you. And I did my PhD in Vancouver, so I'm very happy to be back here. I have lots of memories of the city. I would also like to, can you see the mouse? Okay, yeah. So I would also like to thank two key people who have helped me prepare this presentation. So Roman Bachman and Xiangmeng Meng. They're both members of our group at Riken AIP. So the topic of this tutorial is deep learning with Bayesian principles. And my goal today is to sort of bring the two communities of Bayesian learners and deep learners together, and just to show you how one can sort of see same set of principles explaining the two different communities, the ideas from these communities, and then because of those principles, these ideas can be combined. And I have been doing so in my research myself, and I just wanted to start with giving you a little bit of motivation of why I've been interested in combining ideas from deep learning and Bayesian learning. So my goal, like perhaps many of you in this room, is to understand the fundamental principles of learning from data and use these principles to develop algorithms that can learn like human beings, like living beings, like animals. Okay? And I find that combining ideas from deep learning and Bayesian learning has been very useful for me to write algorithms that can learn like living beings. So just to give you an idea of what I mean by learning like human beings and living beings, I show you this video of a human learning, and this is my daughter when she was 6 months old, and she's trying to gain experiences about the world. She's trying to figure out what she likes, what she doesn't like. So she touches here and there. She's collecting small chunks of data by interacting with the world, and she's figuring out that most interesting part of this ukulele is the sound that it comes from. Everything else is kind of less interesting. So the amazing thing about human learning is that we continuously interact with the environment, we get this small feedback, and we continue to learn and improve our knowledge about the world. And if we're given some time, so this is like 6 months after she's figured out what she likes in the world, and she's able to generate these experiences that she finds pleasant. Right? And everything else is irrelevant. So this is really incredible, and we don't really stop here. So this is after 2 months. She has kind of transferred her knowledge from a ukulele space to a guitar space, and now she's generating the very similar experience that she enjoys. Right? So the amazing thing about how we learn, how people learn, and how animals learn too, is that we're doing this type of lifelong learning. We're continuing to improve our knowledge of the world and figuring out what we like in the world, what we don't like, just through small chunks of information. So we really get to interact, slowly with the environment, and through that environment, we can learn. And even when the environment changes around her, so from guitar to ukulele to guitar, we can still continue to improve our knowledge, and we can adapt and adjust. But this is very different from the kind of learning that we see in machine learning right now. So deep learning is really bulk learning. So we believe that everything that we need to generalize in the world out there, it's all present in this large amount of data in front of us. and then we suck all the knowledge from there into our network. So we sort of assume that everything is stationary, right? So I find this gap, to be troubling, and my research is kind of focusing on bringing these two things together. And when I think about what is the best possible, mathematical framework that explains human learning, then I turn towards Bayesian learning. So there's many works before that people have done in neuroscience, in evolutionary psychology, in economics, to show that the way that humans learn and animals learn, this can be described with this kind of sequential update that we have in the Bayes rule, right? So my interest in Bayesian learning and deep learning basically comes from this kind of thing, that I want to design lifelong learning system that pretty much like how people learn, how animals learn. And for that, I take inspiration from Bayesian learning, and I want to put that into deep learning. So today I want to kind of share what I have learned in this, and what many of you probably realize, and maybe that's why you're here, is that Bayesian learning and deep learning, they look very, very different from each other. So Bayesian learning uses these kind of Bayesian models where the goal is to be able to, generate the data, so write the data generation mechanism. So use some fancy models like these, like probabilistic graphical models. But then deep learning, this is more like principle of trial and error. So you write a loss function, you have a model that can predict the data quite well, and you sort of look into this, minimizing this loss, right? So here you can do kind of stochastic training, where you're looking into gradients, a very local information, and you're taking steps according to that. While in Bayesian inference, once you're given the Bayesian model, you invoke this Bayes rule, and you have to do a huge integral, and that's very, very difficult. So if you compare the two types of learning, they're really complementary to each other. So deep learning works quite well for large data and complex models, and it's really scalable. But Bayesian learning is really failing there, because you have to compute, Bayes rule, you have to compute this integral. While for deep learning, it's very hard to compute uncertainty. So to know what's happening away from the data, to really know what you don't know, there's no mechanism, indirect mechanism, at least in the loss function that you write. But Bayesian learning is really good at that. And because of this, because you know what you don't know, you're actually able to update your knowledge with time. So the sequential updating, active learning, or online learning, or learning from incremental information, the one that we require in lifelong learning, it's really kind of possible with Bayesian learning. So the two types of methods, they're very different, and they have complementary strength. So the question is, how do we bring these two things together? So that's my goal to talk about in this tutorial today, is to combine these complementary strengths of two fields, not to kind of improve some of their aspects, but to solve challenging learning problems, to go beyond what's possible with each of those, to do this kind of lifelong learning. So that's going to be a running example in the tutorial. Okay. So the main idea of this tutorial is, which I call deep learning with Bayesian principle, is to sort of take the Bayesian principle from the Bayesian learning and try to see it as a general principle that can explain both Bayesian learning and deep learning. Okay, so bring the two fields together at the same platform, same footing. So we have same common principles for them. And then we can, once they're at the same place, we can sort of combine strength to design, improve, and generalize learning algorithms. So that's the main point. And what's going to happen is that we're going to do this by starting with the Bayes rule, with the Bayesian principle, and then doing approximation to them. And if you do a clever algorithm, it will somehow let us kind of see everything, derive everything from the same principle. So we're going to write a learning rule. It's going to be Bayesian learning rule. And it turns out that deep learning algorithms would just be a special case of that, and many of them that I've listed here, but also Bayesian learning algorithm like Bayes rule and many other approximate inference algorithms that we use can also be derived from the same principle. Then once things are same, then we can design new deep learning algorithms to estimate uncertainty, to do something that we can't do directly with our deep learning framework, to understand the importance of the data, and then to see how these two things can actually help us take us towards lifelong learning. Okay? So that's the goal for today. And what I want you to remember in the end is that in this tutorial, the goal is to put everything at the same place, to talk about principles that explains many things in these two different fields, and then try to combine strength with that. So I didn't really call it Bayesian deep learning for a purpose, because my goal is to kind of take the focus not from these individual methods like improving Bayesian learning using deep learning or improving deep learning using Bayesian learning. Rather than doing that, I want to focus on the principle, so zoom out a little bit, and then solve the bigger challenging problem like lifelong learning with this. So that's the focus that we have, so that's why I didn't call it Bayesian deep learning, but under the hood it's kind of very similar. The goal is to bring the two communities together, and I'm not really going to go into the details of, lots of amazing work here in Bayesian deep learning, approximate inference, Bayesian inference, uncertainty estimation, generative models, GPs, and neural network. There's a lot of this stuff there. But I'm not going to go into the detail of these methods. Rather, I'm going to focus on principles to put everything at the same place. Okay? And I hope you enjoy that part of it. And I might not have time to discuss many things that have happened, and I'm just one person, and arXiv goes crazy these days, as you know. It's very hard to know. There are lots of things happening, and I'm definitely missing a lot of stuff, and I apologize beforehand for that. And if you think I should have included some of these things, please contact me, and I'll try to do a better job next time. And the other disclaimer that I have is that the tutorial is really, really biased. It's really based on what I know the best, and it's based on my own expertise. And I try to do a kind of tutorial or overview of these things, but it just ended up being most of the things that I knew. So I'm sorry for that. And half of the slides are basically talking about my work. So there's still a lot of things that are, hopefully there is a perspective that's bigger than just kind of doing this advertisement for my own work. So that's not my goal, and I hope you understand, and I apologize if I offend people. Okay, so with that, do I have water, please, Chang? Yeah, I was sick before coming here, and I'm still kind of recovering from this. I hope I get my water soon. Okay, so let me start by talking about the two things, deep learning versus Bayesian learning. What are these things that I'm talking about, and how are they different, and why is it difficult to put these two different types of learning paradigms together? Okay, so deep learning is a much simpler thing. So we all probably know about this. So it's based on frequentist idea. So if you're given some data and you have some model with parameter theta, you write a loss function, and maybe loss function is motivated by this empirical risk minimization or maximum likelihood principle, and you try to minimize it. Right? So it's based on this principle of trial and error, and loss function could look, here's an example, could look something like this. You have a deep neural network, you have some input, you predict the output, then you take the difference between the two, you try to minimize this, but not too well, so you add a regularizer here. Right? This is very, very standard. And this you can optimize just by using gradient descent algorithm, this kind of thing where you compute stochastic gradient or gradients, and then you precondition. Thank you. Okay, so you compute the stochastic gradient, and this is very easy, and it's scales very well to large data and complex model, gives very good performance in practice, and you know, it's everything is great. So the question is, what could go wrong with this type of approach? And I just want to motivate why we should be more Bayesian and not just doing this type of minimization where you only compute one model or one point estimate of the parameter theta. Okay, so I want to motivate you with this very simple example. The question is, I'm showing you some data and I want to fit it. So which model is a good fit? Okay, so this data is basically you know, some kind of frequency of an event. So as you go along the x-axis, the frequency sort of decreases. It's like, you know, 100 times a year, 10 times a year, once in 10 years, once in 100 years, once in 1,000 years. So it's kind of going down like that. And now the question is, if, oh wow, thanks. My PhD supervisor came back and helped me out again, so thank you. Okay, so so here's the data, and I'm basically saying one model possible explanation of this data is this blue line. So it's just a straight line. It's saying everything is decreasing with time. The other explanation could be a little bit of different model where I have a linear part for the first half and then another linear part for the second half, but I have sort of a kink in between. So there is a little bit of discontinuity. Now the question that you're asked, because if you're a frequentist or if you're a deep learner, then you have to pick one model out of this thing, and the question is, which model should you pick? Okay? So how many of you would like the blue model? Can you raise your hand? Okay, a lot of you. And how many of you would like the red model? All right, this is great. I didn't expect this to be same as my class in EPFL. Okay, so it's almost 50-50. And it's 50-50 because it's designed to be. So none of you are actually wrong, so this is great. But I have kind of cheated because I haven't told you what this data is about. But this is reality, you know, we don't really know what the data is about usually. So if I tell you that this x-axis is actually magnitude of earthquake, this is real data from Tohoku, and this is an example taken from Nate Silver's book, you sort of start to get the sense of what's going on here, right? So this is like lower magnitude earthquake and this is higher magnitude earthquake, and you know that this happened more often, and thank God this doesn't happen, you know, so much often as the small earthquake. Otherwise, we'll all be, you know, not doing so well. So if you look into the x-axis, you realize that you have more data on this side and you have less data on this side. And as you go from this side to that side, you have less and less data, right? So you're very confident about what you're saying here, but you're less confident here. But actually, when you're designing your buildings to be earthquake proof, you actually want to be more careful here, right? So you can see that the earthquake that happened in Japan, which was around this point, this blue model is saying that it's going to happen once in 100 years, while the red model is saying it's going to happen once in 1,000 years, right? So the predictions differ remarkably from each other. So if you're a blue model person, then you're more conservative. You're saying, well, it could happen, you know, it could happen in the next 100 years. But if you're a red model person, then you're being a little bit more relaxed about it. And if your goal is to design buildings that are safe, then you want to be more conservative. So you want to know how much you don't know. Okay? So that's the kind of point that red is more risky than blue. And if you don't know how much you don't know, then you sort of missing out. So the Bayesian idea is actually not to just compute probabilities over, you know, not just to estimate one model or two models, but rather to estimate, to try to assign probabilities to all possible explanations of the data. And if you do this, then you sort of start getting this kind of error bar. And if you're a very conservative person, then you're going to, you know, choose a less risky option. So you're going to try to be somewhere here so that you say this earthquake is going to happen once in 10 years, and I just better be safe than sorry, right? So it's important to have this kind of uncertainty. And many people here, because you know, maybe you work in, you know, AI type of application or machine learning type, and you say this doesn't happen in my application, then I would really like you to think more about this, because, you know, when you're, for example, doing self-driving car, you collect a lot of data when you're doing normal driving. But when you're having accidents, which is on this side, you don't know how you're going to fail. So you have very little data. But you actually want to design your system so that you do a better job on not failing, right? And this is all fine. So data bias is a huge problem, and I think the Bayesian inference, the ideas from the Bayesian community, really can help you to, focus more on oh, so much water. I'm so happy. Okay. So yeah, you want to avoid data bias. You want to pay attention away from the data, not just in fitting the data examples. And that's the point of the Bayesian learning. So how do you do this within Bayesian principles? So it's a kind of cartoon of Bayes' rule of how this works. If you're not really familiar with this, well, in Bayesian learning, we start with a prior distribution. So basically we say we're going to generate candidate models. So it's basically like all of these lines. I just blindly just look into all possible models. I generate these lines and then I specify a likelihood. So this is like the neural network, it predicts something, and then I try to match the prediction to the true output. So this could be like mean square error, so it's like a Gaussian distribution, and I define this likelihood. And then likelihood times the prior, this sampling and then scoring, gives me a score. So I say, oh, this line fits it quite well, so I give it a high score, and then if I go away from it, I give lower score because I'm not fitting the data well, so my likelihood is actually taking lower value, right? So I have ranked these things, and I hope that you can see it, that the font is big enough, but you rank this thing, but you don't have error bars because you don't know where to stop here, right? So the idea is basically to use the Bayes rule, and you look into all possible model, you look at that score, you average it, and you normalize things. And when you normalize it, you get the posterior distribution, which gives you this error bar, right? So you want to know how wide or narrow this thing is, and you can't actually find that out if you don't normalize. So normalization, or this kind of averaging over all possible explanations for data, is an important feature of Bayesian principle, and this sort of lets us know what we don't know. So it's a global method. So it's very different from deep learning, where you're computing gradients on the mini batches, which is really looking into the local thing and only looking at one possible model. Bayesian inference is trying to look into all possible explanation that could lies in the support of the prior, and then you integrate and normalize over it so that you can get this kind of thing. So no wonder it doesn't scale, right? Because it is just insane to carry around this weight to think about every possible explanation of your data, and it's very, very difficult. So it's very, it doesn't scale to large problem, but this integral is an essential part of Bayesian learning that makes it what it is. So it's not only uncertainty. I also wanted to give you another example that all of Bayesian deep learning community really focuses on uncertainty. And one reason why I bring lifelong learning or sequential learning into picture is because this whole point of not knowing what happens next actually is important for you to update your beliefs sequentially. So to give you an idea of what I'm saying, think of this type of classification problem. So you have two classes here. And it's again this same trick question, right? There's no right answer here. And I'm asking which line is a good line, right? You could see that both lines actually classify the data very, very well. So the blue line and the red line. And if you are a machine learning person, you probably pick the blue line, right? But you don't know what's going to happen if your world's going to change. If it's a non-stationary world, you don't know what you're going to see next. So because it's a trick question, this is what you're going to see next, right? So if you see the next class to be something like this, then that blue line actually was a wrong option, and the red line was the right one, right? But in the previous world, you didn't know that. You had no idea, when you were young, what experiences you're going to see when you grow old. So how do you make up for the mistakes that you do in your, in your past life? And that's the kind of point. So it's again the same idea. What do you not know, and how does it affect your future? Right? You're young and ignorant, and you made some mistakes. And the idea of Bayesian inference is again the same. Like, I don't want to commit to one line. I want to commit to everything that could exist out there. And this is again insane, but it works in the way that you sample from the prior and you score it and you normalize it. And then you write down your posterior distribution. The posterior distribution is saying that this type of line is quite probable. It's actually really probable, because it's kind of minimum norm or something, but then you're not leaving this other line. This is that I think it was blue line in the previous slide. You're not leaving this other line as well, right? So then once you have this thing, you can now, when you get the next set of data, so this data set, I call it D1 here, and suppose you get the next set of data, I call it D2, then you can just invoke the same thing. So you do the Bayes rule again. You now, instead of randomly generating from prior, now you generate from your previous posterior. So it's basically saying that the lines are going to be, more likely here and then less likely away from it. So all the information in D1 is included in these lines, and now you're just going to update the new belief for these data points. So you're going to score with D2, and then you're going to update. So you're going to get the new posterior distribution. And if you update that, it's going to say, well, these other lines were not classifying the data well, because these data points were classified wrong. So if you could see what's happening, right? So these data points are classified wrong, so I'm going to correct it, and I'm going to make this more probable. But because I'm keeping track of everything, it kind of works fine, right? So if I make a mistake, I can correct it. But if I'm doing just keeping track of only one line, then it's very hard to make up for that. Okay, it's not impossible, but it's hard. So this type of global property, it enables the sequential update. And to summarize what I've been saying is that the two types of learning are very different types of learning, and the fundamental difference between the two actually comes out to be that this being involving integrations. You're looking into all possible things and you're averaging over everything. So it's a global update. While in deep learning, you're just computing gradient, which is a local operation. So it's scalable, it's easier to do. So they're fundamentally different from each other because one is trying to do too much and other one is trying to do too, well, I shouldn't say too little, but trying to be too local about things. And that's why you're scalable here and not here. But because of that, you have uncertainty, and you can do sequential updating here, and there is very little mechanism to do that here, right? So I hope I've convinced you that they have complementary strengths. And now I sort of want to go into the first part of the tutorial, where I want to say that even though these things are very different, if you write the right principles, then you can just derive these two different types of algorithms, methodologies from the same principle, right? And the idea is going to be approximating the posterior distribution. Okay, so the main idea this slide sort of tells you, and there's going to be a lot of math after this, so this is your slide to, before you fall asleep, to remember. So the main idea is to start with a Bayesian learning problem. So start with the Bayesian method, and then you have a posterior distribution, and then what we're going to do is we're going to approximate the posterior, and we're going to introduce a learning rule, which I'm going to call Bayesian learning rule, to estimate this approximation. Okay, and these two components are going to be the key. What's going to happen is that if you change the approximation from a very simple approximation to a complex approximation, you're going to see a variety of learning algorithms pop out of Bayesian learning rule. Okay, so the Bayesian learning rule is this kind of sneaky thing that takes different form, and you can derive these different types of algorithm from it. Okay, so to give you a little bit more specific example, suppose that you have this two-dimensional posterior, so you have two parameters, and you have this complicated posterior distribution, and I say I'm going to approximate with a Gaussian, and a Gaussian where I can only change the mean, but I'm going to keep the covariance to be fixed. So I'm basically kind of can move the circle around, but I cannot change the radius of it. And you can see that I could put the circle here probably, right? So if you try to estimate the mean of this Gaussian using Bayesian learning rule, it ends up just doing something like gradient descent. So it becomes a first order method. It makes sense. And if you increase the complexity of your approximation, let's do multivariate Gaussian, and now you want to estimate both the mean and the covariance, then it'll be something like a second order method, so something like a Newton method, right? So you increase the complexity, the algorithm that you get out of the Bayesian learning rule is a more complex algorithm, okay? And if you continue like this and you do mixture of Gaussian, then you will estimate each of that Gaussian using a Newton method. So you will have, you can guess it, you'll have an ensemble of Newton method, right? So it's just naturally works like that. And there's a lot of things in between, and we usually don't go beyond second order methods, but you could actually, you know, have more flexible posterior approximation. If you can optimize it, then you can fill this gap. And if you continue and you get to the exact posterior, suppose if you could compute it, then the Bayesian learning rule just becomes Bayes rule. Okay, so this is the high-level view of what we're going to see in the next few slides, is that the learning rule, if you write it in the right way, the approximation just does the right thing, that if you increase the complexity of the approximation, you get more and more complex algorithms. Okay, so it almost sounds kind of impossible. I know many people say, oh no, this cannot be true, but I hope you will be convinced in the end that this is true. So let's start with the first building plot. And there's a little bit of math involved in the beginning, so I just would like you to bear with me with the details. And you don't really have to, you know all the details, just kind of know the big picture actually, so it's quite intuitive and simple. But let's start with the first part, which is the approximation. So we're going to focus only on exponential family approximation, and it looks something like this. And if you don't remember the details of this, just think of a Gaussian, which is an exponential family approximation, and a Gaussian with mean and the inverse of the covariance, so it's called precision matrix. It has this quadratic form. If you do a little bit of manipulation of this to write the linear term here and the quadratic term here, then you can call these sufficient statistics. So this t of theta is basically this linear and this quadratic thing, and then the coefficient that you have in front of it is the natural parameter. Right, so this lambda is this natural parameter, these two things, and the sufficient statistic is this. Okay, so you don't really have to remember the details of this, but another parameterization that we're going to use that's going to play the role in the learning rule is expectation parameter, which is essentially the expectation of this. So in the Gaussian case, it's going to be expectation of theta, which is the mean, and expectation of theta transpose, which is the correlation. So it's the two moments. Okay, so just to summarize, I give this to you here, and you don't really need to know this detail. What you only need to remember that we're going to have an exponential family approximation, we're going to have a natural parameter, we're going to call it lambda, and we're going to have an expectation parameter, which we're going to call mu. And these two are two different parameterization, and we are within this kind of approximation. Okay, so don't need to know the details really, just remember lambda and mu. Okay. So now you have the approximation, and now I'm going to introduce the Bayesian learning rule to estimate the parameter of this approximation. And this is the second step, and after this we'll be done with the principle. Okay, so deep learning algorithms optimize this type of loss function, and we use this kind of algorithm. But what I'm going to use more of a Bayesian flavor, so an optimization problem that looks like this, where I'm optimizing over distributions. So this q of theta is this exponential family approximation that I just talked about in the previous slide. And what I'm doing is I'm doing a little bit of more Bayesian thing. So it has a Bayesian touch here, that I'm not looking at the loss only at one point, but I'm looking at the loss sampled, from this distribution. So ideally, these are kind of these lines that I was showing in the previous examples, and these lines should be sampled from the posterior distribution, but you don't really know the posterior distribution, you're trying to approximate it. So you're going to use the approximation. Okay, so it's just kind of a Bayesian thing, and I'm adding an entropy penalization because I don't want the distribution to collapse to a delta, but I want to keep some diversity. And you will see that this is actually very related to Bayes rule, and it's actually equal to Bayes rule under certain condition, but we'll defer that until we have kind of derived all these learning algorithms, okay? So I just want you to bear with me that I'm going to optimize this objective for some reason, versus this one that we use in deep learning. Okay, so I'm going to write an algorithm very similar to this, and I call this Bayesian learning rule. So there are several parts to it. So I'm basically optimizing this objective, right? So this is written here. And now this objective is a function of the parameter of Q, because I have averaged out theta. I have done this Bayesian thing where I've taken averages, this global thing. So now this depends on lambda and mu. So I'm going to update lambda, which is the natural parameter, but I'm going to do a weird thing that I'm going to take the gradient with respect to the expectation parameter. Okay, so it sounds very weird at first when you look at it and you say, why are you doing this? And this has relations to information geometry with mirror descent algorithms and with natural gradient methods. But let's do that later on. For now, just accept it that this is going to be the rule that will kind of give us deep learning algorithms or optimization algorithm as a special case. Okay, so we're going to work with this algorithm that optimizes this. Okay, so we are almost at the end of the principle. So the principle is actually involves of two steps. You choose an approximation, Q, so you choose an exponential family like Gaussian, and then when you want to optimize deep learning algorithm, you know that they're local. So you want to be non-Bayesian, so you give away your Bayesian property. You say, Bayes go away, right? I'm going to not be global, I'm going to be local. So we will do these two tricks, and then the principle just does the trick, and it gives you all kind of flavors of algorithms out of it. All right? I hope this makes sense, and I'm now going to go into showing how this is a very general kind of algorithm that subsumes lots of these types of algorithms. So the first part of the next topic on deriving many existing algorithms, we're going to look into deep learning algorithms, and we're going to go through gradient descent and then stochastic gradient descent, then Newton method, and then we'll see RMSprop is related to that, and then adding momentum will give us Adam. Okay, so we're going to do this first part. All right, so let's start with gradient descent. It's a very, very simple algorithm. You update, go in the opposite direction of the gradient and you update things. And the claim is that you can derive this algorithm by using a Gaussian approximation with fixed covariance. By the way, all the slides are online on my webpage. I forgot to tell you this. And these things that I'm deriving in next few slides, I have been trying to write a long paper, but long paper takes a long time, I realized. And so it's not complete at all, but I put some derivation that I'm using in this, tutorial in this place on my webpage. You can find it on my webpage, so you can see some of these details if you don't follow everything here. Okay, so what we're going to do is we're going to derive gradient descent, and my claim is that I'm going to choose a Gaussian approximation with fixed covariance, and I've written a scalar case here. So the covariance, I've chosen it to be 1, but it could be anything. It doesn't change the derivation. And I'm going to just estimate the mean. And then if you write the math, it turns out that for this case, when you don't have the covariance here, natural parameter is just the mean, and expectation parameter also is just the mean. So you have just kind of first order information, just the first moment here. And the entropy is just constant. So this is actually a very, very simple one. So you take the Bayesian learning rule, you plug in lambda and mu in here, you realize that entropy is constant, so it's going to go away, and if you do all that, you get that. Okay, so I'll pause for a few seconds to just let you see that lambda is just m, mu is m, and then entropy goes away, right? So it's the algorithm already looks very similar to gradient descent, but what I'm doing here is I'm doing some kind of global thing. I'm trying to ask information about the gradient of this through a distribution. Okay, and this is the key. So if I say Bayes go away, I'm going to do an approximation. I'm going to basically approximate this loss not at the samples from Q. So I'm not going to look at the various line, I'm only going to look at the mean. Just this local thing that I'm doing. And if I make that approximation, it's quite straightforward to see that you get that algorithm, right? So this is a very toy example, and many Bayesians in the room might be saying like, yeah, I know this, but next example will be a little bit more tricky, right? So I hope this convinces you that if you do these two things, that you choose the right approximation, then you don't do the Bayesian thing, then you get the non-Bayesian algorithm, which is what you would expect. It's very intuitive in that sense, okay? So if you do stochastic gradient, you want to do dropout and all of that stuff, you can get all of that also out of this if you just replace the gradient by the stochastic gradient. Okay, so I'm going to leave it at that, and I'm going to go to a more tricky example, which is the Newton's method. It's a little bit more difficult to see why it will pop out of this, but we're going to choose the right approximation. So in this case, we're going to do a multivariate Gaussian, and as I showed you before for Gaussian, now you have mean and the inverse of the covariance, so this is the precision, and the natural parameter and expectation parameter look like this, right? So we're going to do the same kind of trick. Let's start with that. Well, you have this entropy term, and I'm going to say that this term actually goes away and becomes very simple because of this property. I'm not going to prove it, but just take my word for it that the gradient of this with respect to the expectation parameter is just a natural parameter. It's really, really beautiful actually. It has a lot of things to do with Bregman divergence and the duality between the lambda and mu, but we're not going to go into that. Some of these things are actually discussed in this paper, but if you take the gradient and you plug this in here, then so you basically what I've done is I am just kind of replacing this h by this lambda, okay? And then I can move this lambda to this side. Sorry, a little bit of more math here to get this thing. So I've just done, oops, what am I doing? Just done a few manipulation here. Start with the, go back. Start with the entropy, put the gradient there, move this here, and that's still the Bayes rule, okay? So now we are ready because we know lambda and mu, and we know the loss. We can just plug things in, and we'll do the same thing that we were doing before, okay? So let's start with the first natural parameter. I put it here. Sorry, this is a tricky example. It takes a few more steps to get to it, but there is an insightful thing here that will come in the next slide, and I'm getting to that soon, so be patient. So I'm taking the first natural parameter, putting it there, taking the gradient with respect to the first expectation parameter, just turning the crank. Do the same thing with the second natural parameter, taking the gradient with respect to this guy, okay? Just simplify a little bit, put the 2 in this side. So you see that I have 2 natural parameters, and I have 2 expectation parameters, and I got an update, right? Which is doing this kind of moving average, all right? So you look at this, and you look at this, and you go like, this doesn't look anything like this. This is expectation of L, and taking the gradient with respect to this and this. There's no Hessian. There's no gradients. So what's going on and how are we going to get there? Right? So luckily, we're going to do a little bit more of simplification of these things, and this is where the insight comes in, that these gradients are actually really, really special, okay? And there is an identity, it's called Bonnet and Price and identity, and there's some reformulation, and many people have actually written about this for many years, but it turns out that the gradient with respect to the expectation parameter, it can actually be expressed as gradient and the Hessian of the original loss, okay? So the math is complicated here, but what I want you to remember is that when I was doing, as just the Gaussian with the mean and the covariance fixed, I got this to be approximating the gradient, right? So it was the first order information, but now I've added an additional component. I've added a second moment. And the second moment basically lets me ask questions, a query about the Hessian, so the second order information. And this is my point. If you add higher order information to your sufficient statistics, going from a Gaussian with only the mean, then going to a Gaussian with mean and covariance, you have second order information, then you start asking questions about the gradient and the Hessian. And so principle is about using this expectation parameter, and the gradient with respect to the expectation parameter basically lets you ask questions about higher order information about the loss. And this is why increasing the complexity gives you higher order methods. Okay, so After this, there's a lot of mathematical manipulation, and they're all there in the appendix of this paper. And if you do all of that, and then you say, okay, I don't want to be Bayesian, I want to be local, you do the same kind of thing. You just approximate these expectations at the mean. Then this becomes the gradient, and this just becomes the Hessian, and you get something like this. Okay, so I'm not really explaining the detail, but you could sort of see how from here and here you'll go. The second line is almost the same. Basically, this gradient is just replaced by this Hessian, and you're just doing a local thing, so you get that thing. Okay, so my goal here to give you kind of intuitive idea of why this is happening, and I wanted to go through the proof because it's important to see that principle just kind of follows through, that these gradients gives you this gradient and the Hessian, and you're doing this kind of moving average and computing the precision, and precision is then used to scale the gradient. So now it's looking a little bit more like Newton, where you're computing the second order information in the precision. So the covariance tells you how uncertain you are, and that's related to the Hessians that you've seen in the past. You know, it's a moving average of things. And if you were in a nice convex regime where taking a Newton with step size 1 makes sense, then you can just kind of set the step size to be 1. And if you do that, then this goes away. And this S becomes just H, and you get the Newton's method. Okay, so what the principle is actually telling you is that you're very certain that the Newton type step is a good thing to do. Then you just do a step size of 1, and this rule gives you the Newton method. But if you're not sure about the second order method, then the principle says that you should be doing this kind of moving average. Okay, so I hope that this convinces you to some extent that there are two parts to the principle. First is choosing the approximation, then doing this kind of global to local thing, and then you get the optimization algorithm out of it. And if you increase the complexity of your approximation, you go from first order method to second order method. Okay. So how do we get to deep learning from here? And it's actually quite straightforward once you have gone to first order and second order method. So I've contrasted here RMSprop with the thing that we just derived in the previous slide. And it's incredible. And you look at the updates. This is with the multivariate Gaussian. So this is this matrix. This is the precision. And this update essentially looks very, very similar to what you have in RMSprop. And really, this has taken the community a lot of time to figure out through lots of empirical evaluation that we should be, computing this kind of square of the gradient and taking a moving average. And we have stochastic, gradients. So these are really noisy information. So we should be smoothing them out by using this kind of moving average. But this just comes out of the principle, You don't have to do any other work here. So it's very, very nice to see that this type of thing just comes out. And the difference here now is that this is a matrix, while this is usually a vector, right? So so what you can do is you can do some approximation. Then instead of choosing the Gaussian, now just use a diagonal covariance. So this is this in-between thing. If you use this to be a diagonal covariance, then this matrix will become a vector like this. Then the Hessian is there, and you don't want to compute the Hessian because it's very expensive. Let's just approximate that by the square of the gradient. And this is called a gradient magnitude approximation, and there is a reference in this paper that actually really goes into the detail of what are the implications of using this approximation. And the key point here is that it is sort of giving away the second order information and just looking at the magnitude of the gradient. It's simple to compute, but it's really not a second order information. So you're not doing a second order method, you're doing something really approximate. And then you want to use the scale to scale vector to scale things, so pretty much like here. But now the scale vector contains the sum over all of your data examples which are inside this, and you're taking the square of it. So actually, this lets you to kind of double counting your data examples, and because of that, you might want to do square root. So there is a really nice proof in the paper here If you look into that, then you realize that, okay, this is kind of a bad idea. You should do square root. That's one way to explain this kind of square root thing here, which doesn't come out of the principle here, right? So you do a bunch of approximation, and then you can get something like RMSprop. So the point of all of this is that you can get these algorithms all from the same principle, and to get this kind of scalability, you have to make certain approximation. To get this local algorithms, you have to give away the Bayesian principle. But essentially, the Bayesian principle explains all of these algorithms, and it doesn't stop here. If you take the Bayesian objective, add a momentum term, so this is like a heavy ball term with KL divergence. This is not like your usual momentum that you're adding in the optimization loss, but rather you're doing it in the Bayesian loss. This is given in the appendix E of this. It's a long proof, and it's super beautiful, and I would really ask you to check it out if you read this paper. That Adam just kind of falls out of it. There's just one slight approximation that you have to do. So this is extremely nice that the principle with very little approximation just always kind of makes sense. It's not exact, but it gives you a way to explain many kind of different things. Okay, so just summarize. The gradient descent is derived using Gaussian with fixed covariance and only estimating the mean. Then second order method, like Newton method, is derived using a multivariate Gaussian. And you can do something in between if you did a diagonal covariance and then you made a lot of crude approximations to that. And if you add momentum to the Bayesian objective, you get Adam. So all of these things actually can be explained with the same principle. And for ensemble of Newton method, the details are in this paper. For mixture of exponential family distribution, you have to do a little bit of more work. You have to modify the Bayesian learning rule, but the principle actually works out. And this is what we've been doing over the years, is trying to make sure that things actually all fall in the place, and they make sense when we try to increase the complexity of our approximation. One very important thing is that if you want to do an optimization algorithm, not a Bayesian thing, that you have to go from a global to a local thing, but that might be a bad idea many times, right? So if you are actually okay by being a slightly Bayesian, so then if you want to improve the deep learning algorithm, so then don't do it, right? And that is the kind of point that we will see, that we will have some algorithm that estimate uncertainty, but they'll just run RMSprop and Adam, and they'll add a slight Bayesian touch to it by improving the computation a little bit, but getting uncertainty or getting this kind of sequential updating going with that. So I hope that all of this made sense to you. So we have finished this part until deep learning now. And I'm 5 minutes delayed, so I'll try to speed up at some point a little bit more. But now we're going to try to see why the same learning rule, even though I call it Bayesian learning rule, why does it give us exact Bayesian inference? Why does it also explain Bayesian learning? How you can obtain Laplace approximation and variational inference of special cases of the same principle. That's the second part of bringing the two communities together. So let's think about the exact Bayesian inference. What I showed you before is that you have this kind of posterior distribution, and you have this normalizing constant here. And what you can do to derive this Bayes rule as a special case is that you define the loss to be, negative log of this joint distribution. Okay. So just take the loss to be your negative log joint. It's like the map estimate that you compute. And then if you plug that into this objective function that I was using before and optimize it over all distribution, that means don't restrict it. Okay. So this is what you would expect. If you let the approximation be anything that it could be, then there's no restriction, then you should go to the posterior distribution. And the proof is actually quite simple, that you write this expectation of loss, and then you write the entropy. Entropy is a negative of expected value of log Q. So this guy is just that. And then you put these two things together. You do a little bit of manipulation to write Q divided by this e to the power negative L. is something that's called Gibbs measure and other things. In statistical physics and many other communities, this is known. You could see that this quantity will be minimized when you set Q to be equal to this. So that'll be 1, and log 1 is 0. That's the minimum value. So Q star that minimizes this problem is essentially the Gibbs measure. Right? And in this case, we've chosen the loss function to be that. So if I plug that in, I basically get it to be proportional to the joint distribution, which is proportional to the posterior distribution, right? So this is very, very simple. It holds, you know, when you choose the loss like this. But guess what? Good news is that the loss could be anything. Okay, so this point I think has been missed a lot in the community, and even if I talk to Bayesian statistician, it turns out that this has not really been explored a lot. So this work actually goes back to 57, and I'm going to tell the references in the end about this, but from the classical paper of E.T. Jaynes, on maximum entropy principle, and the same thing sort of comes back many times by Zellner in 88, and it's been revisited by some people from Oxford, I believe, and they're basically showing that this loss function could be anything. And this construction of splitting the expected loss plus entropy is actually a general thing. And if you follow a coherence property, this is really the optimal thing to do. So all of this idea of rationality within Bayesian inference, it kind of holds for a much more general class than just using a probabilistic model. So you don't really have to restrict yourself to describe your data generating mechanism to be able to write your Bayesian model. You can just start with a loss function. And if that loss function happens to be the log of joint distribution, then you just get Bayesian inference, right? So this actually makes you a little bit more relaxed and more open about things, less religious, I believe. And you know, you can take that and you can then substitute the P by a restriction Q, and we get what we were doing before, right? And then this is actually known as an approximate inference method in the Bayesian learning community, and we always call it variational inference. And when we are a variational inference person, actually I've been labeled as a variational inference person, and it's not really, I mean, people put you in this box and in this corner, and I think that's very, very bad, you know, I think for the community also. What I'm trying to make the point about is that if you use this learning rule, it's about algorithm. How do you optimize it matters. If you optimize it in the right way, it enables you to derive many more things than just variational inference. So you don't really have to do variational inference. You could do, you know, optimization, and you can do many other things, including the exact Bayesian inference, which is the Bayes rule, right? So this is not just a method. This is a principle of how you go beyond. You don't want to just compute the posterior distribution. If you want to compute point estimate, you can do so with this principle by optimizing this. And this is why I don't really call this variational principle, rather I call it Bayesian principle, because it subsumes Bayesian learning as well. So I hope that makes sense to you. I just want to give you a little bit more concrete example from conjugate Bayesian inference, where you can compute exact Bayesian inference. So there's beautiful insight of why this actually reduces to exact Bayes rule, and why everything that we've been doing in the Bayesian world in linear model and Kalman filters and HMM, when we compute these messages in forward-backward algorithm, they're actually gradient with respect to expectation parameter. So we don't realize this, and I just want to show you that this is quite general. So as before I said, take the loss to be this thing, and in this conjugate Bayesian inference, the word conjugate basically means that when you multiply these two things, they both have, you know, they both can be described with the same sufficient statistics. So it's like T of theta. So you can write this joint distribution, log of joint, as split into two parts, one that depends on theta, and that's just the sufficient statistics, and that's the same for the two things, and the other one that depends on the data. And that's what the word conjugate really means. Okay, so it's just the sufficient statistics of the Q. So if you choose a Q appropriately with that sufficient statistics, you will eventually get the Bayes rule. Okay, so if you don't agree with me or don't follow what this means, just think of least square. So this is a Bayesian linear model. You have quadratic loss plus some regularizer. If you do a little bit of manipulation here, you can actually write it as a linear term and a quadratic term. Right? So this is the sufficient statistics of a Gaussian, and the term in front of it is this lambda d that only depends on the data, and it doesn't depend on theta. Okay? So with this nice thing, now if I want to compute the expectation of the loss, I see that it's actually linear in the expectation parameter. And this is the beautiful thing, that if it's exponential family, then everything is sort of linear in the sufficient statistics, log linear, and then the expectation of the loss is linear in the expectation parameter, and so the gradient with respect to mu is just lambda d. Right? So in this case, it will be like this matrix and that matrix, and that's what you need to compute least squares, for example. Right? When you do the ridge regression, you invert this, multiply by that guy. Right? So if you plug that in the Bayesian learning rule, well, you have to do, the trick that I showed you for the Newton thing, that you have to just kind of get rid of that and write the one that, the gradient of the entropy is just lambda, and then you sort of see what's going on here is that you're trying to optimize this to get lambda, but lambda d doesn't depend on lambda, so you have a closed form solution. So essentially you can just set lambda star to be lambda d, and that gradient goes to 0. Okay? So the solution of this conjugate problem that we have been doing is essentially setting this thing to be equal to the natural parameter and computing, least squares solution actually is doing that, computing messages in Kalman filters with forward, backward, Kalman smoother actually, and hidden Markov model. They're all computing these gradients, this lambda d, and we've been doing this without knowing, right? So it fits within the same rule, and the generalization forward, backward for all these conjugate models. In stochastic variational inference, you do the same thing where you choose the family to be split across a global variable and a local variable. And for the local variable, you choose the step size to be of size 1. For a global variable, you don't do that, and you let this be like this, and this is the update that you get. Right? The same thing with variational message passing. There, you choose row to be 1 always. And this all proved in this paper is from 2017. All of these stuff, they're actually Bayesian learning methods, and they can be seen as a special case of this Bayesian learning rule where you compute the gradient with respect to the expectation parameters and you update the natural parameter. Okay? So we don't stop here. You can derive Laplace approximation, a very crude approximation, not variational inference, from the same principle, is that just run the thing that I showed before, just run that Newton method, right? And if you keep running this, maybe you compute stochastic gradient, stochastic Hessian, or you do something like that, but essentially this update will converge to the mode of your log joint, and then this quantity will converge to the Hessian, right? So eventually you're doing Laplace approximation by using the same principle, and you're giving away the Bayesian stuff. You're not doing gradient with respect to the expectation, but gradient at the mean only. So you're going to do this local thing. So I just want to reiterate what I said. This principle that we're talking about here, they're general ways to derive learning algorithm. They're not variational inference methods only. They're ways to derive Bayesian methods, approximate inference methods, to derive deep learning methods, to derive optimization algorithm, and we should not call them variational inference. We're doing them a disservice by limiting ourselves to this small place. So my hope is that by focusing on the principle, we see that these different flavors of algorithm are all very similar and can be explained from the same common set of principles. Right? So I've been doing this for a while, and what I've told you today is this, and Laplace method, and this, and SGD, so under the red circle, but I haven't covered other things. But many algorithms in reinforcement learning, continual learning, and online learning, and global optimization algorithms are related to this, and in the end I'll sort of give you a list of references of how these things are related. it takes a long time for me to write all of this. I hope to write everything in this paper, and right now it's not there, but eventually it will be. So this paper will sort of, put connections between these different types of algorithms that exist in these different fields, and they're all sort of connected through one equation, which is this, where you can choose a different approximation. Okay, so we are at this place. What we have done so far is that we have introduced the principle, and we have shown that by choosing different approximation, we can derive many of these algorithms, and we can also derive many of the exact Bayesian inference and approximate Bayesian inference methods. But now let's go and see why would this help me to do something else. Okay, and the main idea is basically just relax this, assumption of local approximation. Go do something more global to try to sample around your mean a little bit more. And if you do this kind of idea, then you start doing, more things that are trying to improve aspects of deep learning, right? So first part, let's look into the uncertainty estimation for deep learning. And there is a huge amount of literature on this, and they're all kind of focusing on this idea that we shouldn't be choosing one model, but we should be looking into the error bars around this. So this toy example that I showed you before, and why this is important, and why we want to make sure that we focus on our failures and not only on our data, try to avoid biasing our algorithm towards the data that we have collected. So this has been actually used quite a lot in Bayesian deep learning community. So, Alex Candle and Yaron Gall and Cipolla have this really nice paper where they show an example of this, of how this could be useful for examples like self-driving car, where you want to do segmentation. So this is kind of image, and the true segment that you want to find out, like, this is the road, this is the sidewalk, and this is sky, these are buildings, and this is an important information. If you run a deep learning method, then you get something like this, and it looks kind of similar, but if you look closely, you actually miss certain parts of this, right? So you're missing parts of the sidewalk, and you don't really realize this. And if you just have one model, one network that predicts this thing, you don't really have a way of telling if you're wrong or not. Okay, so you could be overconfident, and what they try to do is that they use a method called MC dropout, where if you change the code slightly, then you can sort of estimate the uncertainties of these two types of uncertainty that they have here, and you can get some idea of where you're not doing a good job, and that could help you to not take your self-driving car into the sidewalk and hurt a lot of people. Okay, so that's the idea, and there's lots of work, and there's a huge, Bayesian deep learning workshop, and there's lots of work coming out of this, and I really don't know everything here, even though I try to read a lot, so I just kind of highlight some of these. One line of work that has been extremely popular is just to take deep learning and just keep running the standard deep learning, so don't affect their performance, so they converge to some very good solution, and then use some ideas to drop out, so drop out some of the weights in the neural network, and if you do that, then this somehow corresponds to solving this Bayesian problem. It's an approximation to that, and you can use this as multiple explanations to your data. So you drop out weights, and you get this many models that explain the data, and then you do averaging based on that. So it's a very simple idea, and this works quite well, and people have used this quite a lot. There's another paper, this one, it's a method called SWAG, where they're looking into these points at the trajectory of SGD, and they're averaging over those points. So the point of all of this work is to basically get averaging somehow. And then the goal is how do you choose this averaging, right? And so you can take your solution, the deep learning solution, you can perturb it slightly, either using dropout or using the noise in your stochastic gradient, and that gives you some exploration, and that helps you to, you know, not be really overfitting too well. So this scales very well to large problem, but the kind of distribution that you're building, you know, if you think about the principle, then SGD corresponds to a Gaussian where the variance is not really controlled. Right, so the variance is a free parameter, and you could choose it to be whatever you want it to be. So you're not really paying attention to how do you estimate it. So you're getting some perturbation, like you're getting kicked out by somebody. You know, it's like these Boston Dynamics people kicking the robot, basically to test it, to give it, you know, how you can fail. Look at that place where you haven't seen the thing. So you have this multiple explanation of the data. And these methods are basically trying to do that. And they're trying to do this because they don't want to break deep learning. You know, they don't want to break the performance of deep learning. So this is done in a really kind of good spirit. But then, you know, because you're trying to stay within deep learning, you're not really flexible. You can't change the approximation that quickly. There is some work by the people who've written this paper where they do structured approximation, low rank approximation. I think you can sort of build these things to be more flexible, but for now, you know. There's no connection to the principle, so hope that there will be more work on that, connecting it to more flexible approximation, giving you a better result. And this is where the dilemma comes in. So when I started working on this field, actually, I mean, I was working on variational inference quite a lot, and there the kind of algorithms that we use is basically very similar to what I have just showed you today, but instead of taking the gradient with respect to the expectation parameter, you just do natural parameter. Actually, you could use any parameterization that you want, oh, sorry, the reference is wrong. This should not be 1, 2. This should be 4 and 5. So very nice work by Alex Graves and Charles Blundell on this, and many other papers have been written on this, and they're all of this sort of flavor, and they differ in how do you compute this gradient. And this works fine because now you're not, you know, here you were not flexible, but now you can choose a distribution to be like Gaussian, to diagonal Gaussian, full Gaussian, structured Gaussian, mixture of Gaussian, and all of that. But the issue is that if you run these methods, they don't really scale well. So you have an opposite problem that you're putting the Bayesian principle, but your algorithm looks so different from what you're running here. So you actually break deep learning, you know. And because the two communities are so different, if they're not running on the same principle, it's very difficult to put the ideas together. So this has been an open problem for some time, and only recently we are seeing some more result on this. But this type of update is very difficult to scale to large problems. It's very unstable. I wanted to say one more thing, but I can't remember right now. Okay, I'll just let that go. Okay, so what we actually did recently, and there's a paper from us at NeurIPS, is that we tried to fix this thing. And the idea is actually not that the method is great, but the idea is that we are basically taking Adam and we are just relaxing this local property. So we're just going slightly from local to global, and instead of taking, you know, just the gradient and the mean, I'm taking the gradient at several samples from the distribution. And this algorithm, we called it Vaughan, and I'll give the detail in the next slide, but this helps us to scale it to ImageNet. And because our algorithm is very similar to Adam, the algorithm, you know, we're able to use all the tricks. So if you look into this classification example that I showed you before, you know, you see that Adam is this blue line, and Vaughan, this Bayesian algorithm, is sort of looking a little bit into more solutions. These are samples from a Gaussian, and you're trying to see other explanation of the data. So you see that it's trying to fill the data space, right? It's trying to see, what if I didn't use this classifier and I used something slightly different? What would happen? What would change, right? So it's asking a little bit of more. And if you have this kind of thing, then you get this uncertainty, right? So, so you know that there are other possible explanation of the data, and you shouldn't be very sure of your prediction at these places, right? So this actually works because of principles. Okay, so this paper, Practical Deep Learning with Bayesian Principles, and I'm really sorry to advertise our own work, but I wanted to make a point about what this principle brings to the table. And the idea is that, you had RMSprop before, and you just kind of changed a slight thing. So you remove the local approximation. Don't do this, okay? Instead of that, add this one line where I'm computing the gradient, but now I'm sampling the parameters from a Gaussian. Okay, so it's just this one change, and then add some second order information. So remember, this is the square of the gradient in RMSprop, and this is supposed to be Hessian by the Bayesian principle. So I'm going to do something that's called Gauss-Newton approximation, and that's why this is called Gauss-Newton algorithm. Is that I'm going to do square of the individual gradient, and this takes a little bit of more computation than just computing the square of the sum of the gradients, but it's worth it, because if you're trying to estimate uncertainty, trying to estimate the variance of your diagonal Gaussian, then you might want to add this. And there's some small changes, but basically what happens with this small thing, you take that scale vector, you take the prior precision, and that just gives you the variance. Okay, so now you're estimating a diagonal Gaussian with some variances around it, and the variance is just sort of read off the scale vector. Right? And so we've gone to a little bit more flexible approximation here, and the code is online. What we can do now, that we can write this kind of Adam-like optimizer where you just have to change few lines and then some additional parameters, and we can borrow all the tricks of deep learning because the algorithmic forms are essentially the same. So the thing that we basically did is that we made sure that in the beginning of the algorithm it really behaves like Adam, so you reach a good place and then you slowly start doing more global thing. So we try to follow the principle to just let the variance grow slowly to a higher thing, and then you sample around the solution a little bit more, and it just sort of works. So there's a lot of work to be done here, but this essentially gives us quite good results, and this was not really possible with variational inference before, but with this principled method. So what I'm showing you here is this is segmentation, and this is the uncertainty. So higher value tells you that you're more uncertain. I mean, this is not the best result that you can get, but this illustrates the point that these things can really scale to large problems. So we took this and we also ran it on ImageNet, and this is really the first of its kind of result where we get state-of-the-art performance and convergence rate while preserving the benefits of this Bayesian. So the uncertainties are not that bad, and the convergence of this red line here is very similar to Adam. So it works almost the same. The computation time is a little bit more, and I haven't shown this here, but it's in this paper, and the code is also online, so you can check these things. But basically you perform the same in the end. But you converge very similar to Adam. So the idea is not really that this is my method, your method, and this is the best way to do things, and I beat the soda. But my point is that I stick to the principle, and I feel happy about this, and I hope that I could do this more often, and I enjoy my work a little bit more than just kind of beating soda all the time. Okay, and with that, I want to tell you that, the principle is really broken in uncertainty in deep learning. So there are lots of good work, but we are actually struggling as a community to really show that our uncertainty estimates are good, that we are doing something better than what deep learning is doing. So this paper is also at NeurIPS this year. It does a very good job in comparing variety of Bayesian deep learning method, and what I'm showing here, this is accuracy, higher is better here, and this is calibration error, expected calibration error, and lower is better here. So this is telling you about uncertainty, and this is telling you about the performance. And what's going on with these each group in this blocks plot is that you're shifting your data slowly. Okay? So you're shifting your data slowly, your accuracy is going down, but if you're estimating uncertainty, this should really be kind of reflected in your calibration. But you don't really know, you're actually just getting worse. Right? So this is really, really bad. Like Bayesian deep learning methods, they do not really realize that they're actually doing bad when the data is being shifted slightly. Okay, so if the environment is changing, we can't just adapt by just, invoking the Bayesian principle and saying, oh, uncertainty should help me to improve things. It really matters how you compute that uncertainty. And we're using these kind of local approximations right now, and they're really not enough. So actually in this paper, they show that if you did non-Bayesian thing, you did an ensemble, then you're actually the best. So your performance is deteriorating the least. Like the uncertainty that you're estimating, it's actually quite good with this. But then this is a non-Bayesian method. So I think the principle is broken. You would expect that if you're being Bayesian, you're using a more flexible approximation, like a mixture of Gaussian or a Gaussian with structured covariance, then you should do better than a non-Bayesian method. But it doesn't really happen. And I hope that our committee will fix this thing. If you're interested in this topic, Yaron Gal, who's been running this thing for some time, has a really nice tutorial. It's at this web page, and he goes into the details of the Bayesian deep learning method, something that I really didn't do today. So please look into his slides. There's lots of nice slides. And his group also has been doing a lot of work in benchmarks. I think there are other works also that are trying to benchmark the uncertainty in deep learning, and there's a lot of code and a lot of nice thing here. So I think these kind of works are extremely important for us to know, to estimate the quality of uncertainty. And there's a lot of challenges ahead in this field, and I think it's very important because we can't just take these. So 20 minutes. Okay, I'm really far. So I'm going to speed things up now a little bit. But this slide is important. I just want to say that we can't just take these Bayesian principles and apply them to non-convex problem and think that everything will work out. So here the issue is that different local minima, they correspond to various solved solutions. And you can think of them, drawing a line like this, or drawing a line that goes like this, drawing a line that goes like this. And there are multiple explanations of the data. And they sit at different local minimum. And there are lots of local minimum that are not really important. So there are many places, many ways to explain the data, and they sit at many different local minima. You don't know which one to pick. And the local approximation that we do, they only capture perturbation around these. So they are this kind of solutions that are giving you this type of uncertainty, but they're really missing the whole part in the data space. I don't really know if I should be confident here or not, right? Have I made a mistake? Can I correct this mistake later on? And these local methods don't really give us that flexibility that the exact Bayesian distribution will give us, right? So this is very hard. And one solution that you could do is you could do flexible approximation, but the principle really tells us that if you go to more flexible approximation, we need to go beyond the second order optimization methods. And we're already struggling running second order optimization for deep learning, so how are we going to do this? So this is actually a tricky thing, and this is fundamentally there are things that are missing, and I hope that the principle actually helps us understand this. There is an alternate view that I'm really excited about, and this is going to be the next principle that I will be working on for the whole of next year, another long paper. I don't know when it'll be done, but I want to talk about the importance of the data and thinking about uncertainty, or thinking about what happens away from the data in a different way. Okay, so I'm just going to start with a very simple, this kind of tricky questions. This one is less tricky. So this is a classification problem. There are two classes here. And question that I'm asking is, I've drawn circle around two places here. And I'm asking you which data points are more important for this classifier to be that way. Okay? Is it these examples that define this model, or these examples? Okay, so how many of you think red circle is more important? Oh, wow. How many of you think blue circle is more important? Hey, for once I'm not tricking you, right? So this is correct. So your intuition is right. And this basically, how are you Does your model really know this is the question, right? So when you fit your deep learning model or anything else, does your model understand why it is the way that it is? Does a person understand what experiences make that person, you know? What of my previous examples that I've seen in my life define me? This is really this existential question. And we don't really think about these things. But if you actually put the Bayesian hat on, then you realize that this is contained in your model, okay? And this is the point that I want to communicate in the next few minutes, is that this is what the model sees. The model sees this line. And it doesn't kind of is saying anything more than that because it's in this weight space view. But in the Bayesian community, there's an alternate view, which is called function space view. And if you're from Gaussian process, you know how that works. But you can't do this with neural network, right? So in the function space view, you think about data. Like in SVM, you think about importance of data. But you don't have that in neural network directly, at least not in the weights that you train. But what I'm trying to say is that if you put the Bayesian hat on and if you start putting distribution on things, you get the other side of the thing. So you get this, I call this data view. And it's actually like SVM. It's like the dual view. And it's actually exactly the dual. Although, actually, things that I'm talking right now, they're not really, not all of that is out, so it might sound a little bit confusing. But these two views that I'm showing here, basically I'm showing you that these points are more important. They're actually digged out of this Bayesian principle. And by putting these distribution out, you can bridge the gap between the weight space view and the data space view. It's a model view and the data view. The data view tells you what makes the model that it is. And when it knows what it is, it also kind of understands why it isn't something else. What kind of other data points that could have made it something else. Okay, so it gives you this way of thinking about what it doesn't know. So how do you do this? This is again this paper at NeurIPS, and it's, okay, sorry, I misspelled NeurIPS. But this method that we call neural network to Gaussian processes, where you start with a neural network, and it's maybe trained just with your deterministic method, sorry, Adam or SGD or whatever, you got a line, you can actually just try to convert that line to get a distribution. So do Laplace approximation or do variational inference, do whatever you like, get a Gaussian approximation out of it over the weights, okay? So the Gaussian approximation is this red line, and then it turns out that Gaussian approximations are actually posteriors of linear models, right? We know this. So there is a linear model that is equal to, whose posterior is equal to this posterior approximation. Okay, so find that linear model. You have a Gaussian, find the linear model, and the maths just all works out, and I'm not going to go into the detail, but you're going to convert, you know, find a linear model where the basis functions are non-linear, but it's linear in the weights. So this sort of corresponds, the posterior of this corresponds to the posterior of that, and the details are really in this. But if you do this, then you have a linear model, and you can then convert it to, oops, okay, and then you can convert it to a GP. Okay, so this is the basic idea, that you go to this linear basis function model, and from there you can write the dual of it. So these two things are kind of dual of each other. And if you, you know, I'm not going to detail the math of all this, but essentially what happens is that this posterior approximation, this Gaussian thing that you put in between, it actually helps you the global parameter, which are the weights, to the local parameter, which are data examples. And this is the kind of the dual that you have in SVM. You know, so you have the loss, and if you write the dual of it, and the dual is usually written with Lagrangian, and you have Lagrangian weights, and those things help you to define support vectors. Basically, in this work, that's what happens. Actually, if you want to see the convex version of it, I wrote the first version in 2013. This only works for a limited, you know, class of linear models, but this paper just sort of generalizes the idea. Essentially, what you get is when you use Gaussian approximation to your loss, and I'm not really going into the detail here, but just giving you the insight, you approximate this loss by a quadratic. So it's a linear model. You change the neural network to a linear model,
and you have this, sorry, theta is W in the previous slide, just the neural network weights, and this phi is the nonlinear features that you've got, and you are just doing regression now. But you got these variances that are also estimated from, computing this Gaussian approximation. And if you think out of it a little bit, then you realize that this is the dual variable, right? Because it's like the Lagrangian. Okay, so you see the data points as constraints, and the variances that you do in your Gaussian approximation, you can see them as the dual variable. So the dual variable tells you how important the constraint is. It tells you how important the data point is. So it's just all sort of built in this dual view, right? So you can essentially, use these variances to define the importance. That's the point. And again, you can't do this with SGD or a Newton method, because these quadratic approximations that you compute, they're local. They don't have any global meaning. In a Bayesian version, you're inverting a matrix. You're doing this integration. And that integration helps you to normalize these, importance of each data point. So I'm not really going to go into the detail of that, but just want to convince you with examples. So this is on MNIST. I think I didn't put the right one. This is not exactly the one that I should be showing, but it's a slightly different one. But on the left-hand side, you see the least important one, and this is obtained by sorting the variances. And on the right-hand side, I have the most important one. Okay, and you see that the important one are these boundary points. These are examples. These are misfits that can really change from one class to another class. Right? It's a boundary elements, and the least important ones are kind of lying far away from the. So if the model has done a good job of fitting the data, then you should see this contrast quite well, and you should be able to interpret your result in this way. But this is actually telling you why the decision boundary comes out to be the way it is, because of these examples. They define the model, these experiences. Maybe these are the bad experiences, the memorable one, the weird one that we want to remember that we couldn't do very well, right? So for classification, these are the ones where we fail. The same thing for CFAR10. If you look at the least important one, they're kind of nice looking, pictures, frogs, horses, and ships. But if you look at the most important ones, they're the ones that you're not able to classify, blurry ones, zoomed out, zoomed in, changing different features. So this is there in your model. You're not using this interpretation, but it's already there. You can also compute kernel matrix, and this all in there in the paper. I'm not going to go into the detail, but these days neural tangent kernel is all the all the fuss about. So it turns out that this kernel just is an NTK. It didn't have to do any infinite wide thing. I didn't have to do any asymptotics. Nothing. I just trained a neural network and put a Gaussian approximation, looked at the dual kernel. It's just NTK. So, if you do the right principle, actually, things just turn out to be the way you want them to be, That's my point. So I'm going to skip the part on model selection. It's also there in the paper. But so far what I've talked about is uncertainty and data importance. And let's go to that last leap of the talk. And I have around 30 minutes left. And so I have to finish this very quickly. So let's talk about how these things can actually help you to do lifelong learning and maybe not help you to do that. So what are the challenges to do these things? And I'm going to really talk about continual learning and active learning, and all of these things are not published, and I'm not really up to date on the current state of the art. So this is really going to be very rough, but I just want to give you an idea of all these things that I've talked about, how they can be used to get to lifelong learning. So let's think about continual learning first. So continual learning is this type of lifelong learning where you try to break this standard deep learning setup where you have all the data at once and then you select a random subset, right? So this is what you do in the standard learning. And in continual learning, the goal is to do this sequentially. So you get all the data examples for a subset of categories, so like dogs and cats, and then you train your network on that, and now you're never going to see it again. Okay? And then you're in a different world where you only see lions and tigers. And then you're just going to see that, and then you're never going to see lions and tigers again. So you're sort of not seeing part of the data, and you're doing sequential update. And when you do this with neural network, and this is a very nice paper that actually shows that if you do this in the naive way, that you just run the stochastic gradient algorithm, then it starts forgetting the past data. And it's because there is no mechanism to remember the past information, right? There's no type of this global thing that I want to remember what I didn't classify well, what mistakes I made in the past. And you're not carrying that around with you. You're only carrying around the good stuff. You're this happy person who has forgot a lot of bad things that has happened to you. And that leads to further forgetting in the future, that you're biased. You know, you think present is so amazing that you just live in the moment. Maybe you're a hippie or something. Leaves you to, sorry, no offense to hippies, you're amazing people. But you forget the past because of that, right? You chill out too much. But if you're Bayesian, you actually try to carry this around. As I said before, you plug in the previous posterior distribution, then you carry it out too much, and this become this really kind of not a very sane person that remembers almost everything that happened to him or her. But this is also very challenging because you can't compute the posterior. So this is where we are, right? If you want to do the exact Bayesian thing, it's just impossible. If we want to do like the standard deep learning things, that's not going to work. And we want to do something in between, but then the algorithms look very, very different. We have to break deep learning. We have to write these algorithms that are so different from what we were doing in deep learning, and everything breaks down. So lots of good work has been coming on this side. So this first paper on elastic weight consolidation, this actually took the Bayesian idea and did a diagonal Laplace approximation, actually used a Fisher matrix instead of the Hessian, and then just regularized the weights of the neural network, and they showed that this actually helps. And so this was first paper that actually really used this idea already. And then there's been work in doing structured Laplace approximation, and there's some work on the synaptic intelligence where you're doing something, different from this Bayesian thing, that you're regularizing is using some other idea. And then you try to do variational inference. So this is more of a Bayesian thing, right? So this is a crude Bayesian approximation. It's not really motivated by it, I believe. And then this one is like doing more better approximation. And what I would want to see, so I haven't really talked about many other things that people are doing, but I just put these things because I want to talk about how principle is broken here again. Is that if you go from, a very crude approximation to maybe something more principled, then something that is even more principled, which is variational inference, the performance should improve. Right? That's what we want to see. But if you actually look at the result, it turns out it's not true. So this is very disheartening because VCL is this method that does variational inference, and this is with each task. I'm showing the performance, higher is better. And what I'm showing is that this thick line is when you took all of these tasks together and you jointly train on them. So this is standard deep learning method. So that's the best that you can get, hopefully. And the dashed line is on individual tasks. So you ignored other tasks and you did this, and you really want to be somewhere kind of in between this. If you do Laplace approximation, so this EWC, this is this brown thing, and you're actually doing quite well, right? And it's because you're using deep learning algorithm. You're not changing the algorithm, you're just running it and you're only slightly modifying it. You're still able to do well. But then you plug in variational inference in here and the performance drops. Why? And variational inference is more flexible, so you should do better, right? But this is insane. So I don't understand this. And when I was working on this, it really puzzled me, right? So I think these kind of things don't really make sense because the algorithmic challenges, what we've learned from deep learning is that algorithms are extremely important. And if we change this algorithm, we don't get to the same local minima that we were getting with Adam. So we don't want to change the algorithm. And that's why it's important to see these algorithms with the same point of view. Okay. So we tried to fix it a little bit and we succeeded slightly. So this new method that we use, this Vaughan algorithm, it basically doing variational inference, and it really brings up the performance of variational inference. So this guy goes here, this guy goes here, and then you're here, and you're more or less close. So you fix the principle a little bit by using the better training method, and then you're matching the performance with EWC and sometimes beating it, which is what you would want. Right? You can go a little bit further, and I think I'm going to skip this in the interest of time. So is it okay if I do 15 minutes of question? Okay. So just going to quickly do this, and this idea of what I talked about of like memorable past of what data examples makes you who you are. This is actually another way of doing continual learning, right? So when you're, as a human, when you're learning, you're actually remembering certain things in the past, and that should help you to not forget the past better. So what we did is basically do this kind of human-like operation where we identify what are my important data examples that I've seen in the past, and then try to memorize them, maybe just store them right now, and then regularize your problem just in a very similar way that EWC does. So it's like a functional regularization of memorable past, and the idea is very simple. Suppose I start with the first task, and then I, classify it with one line. Now I get, I have some data examples that makes this classifier good, and I basically remember them. And then when I get the next example, I try to find a line that doesn't perform badly on my past. Okay, so I want to remember the past, I want to perform better, and you just kind of continue this. Then I memorize the important example, I go there, and then I do this, and I continue to learn like that. Okay, so this type of idea, this is another way of thinking about, what I know, what I don't know, what mistakes I made in the past, and you sort of remember certain things from the past. If you realize what was important, what was not important, it's more kind of a human way of doing this type of learning. Then you can actually fix it a little bit more. So if you add it to this chart, it actually, so this is an improvement over EWC because it's doing Laplace. So you improve things everywhere. So this purple line, and sometimes you really do well. So you really get to the best performance that you could have got, but other times you're losing. So a thing that we still need to do is to combine the variational inference with this kind of idea of data points. So we can, with variational inference, we can try to get some uncertainty with a Gaussian approximation. But then by adding data examples, we're adding this dual view, and we're helping to improve the uncertainty, trying to fill the data space a little bit more. So this is a different idea to improve things. Okay, so I have 5 minutes now, and I'm going to skip this part. So the challenges is that computing exact posterior is not tractable. Approximations are kind of don't behave the way that we want them to. So maybe you work with the data space, but there are lots of kind of non-Bayesian solutions, and they're not really seen with the Bayesian principle. And maybe we can kind of put all of these things together, and we can share strengths from these ideas to do something better. Okay. So the summary is that, and I'm going to skip that. I just want to end the tutorial by showing you how you can also not only just look at important data examples after you have trained, but you can actually choose important data points while you're training. So it's kind of same concept of important example, and what I'm doing here is that I'm selecting important example at every step. And I'm doing something like what my daughter was doing in the beginning. So I'm not doing random exploration. I'm not touching all data points at random, but rather I'm focusing on the things that I like. I'm looking into the things that give me a better classifier. Okay, so looking into the important data points, really doing this kind of exploitation. So this example, you have two classes, one is this, another one is this, and what we're going to do is we're going to select the most important example that will be shown with this. And in the beginning, you are just randomly touching, and your classifier doesn't really know, so it's just doesn't know what's important, what's not important. It's just going around randomly searching, and then slowly it figures out, oh, these are the data points I've seen. It looks like I can classify them by drawing a line here. So it's figuring this out. So it's not looking everywhere now. It's looking to improve that current model, and now it's kind of stuck. Some of the experiences are not letting it go, right? So it's pinching the line with these important points that really draw at the boundary. And we're not doing random exploration here, right? So it's really stuck now. So these support vectors, these examples that are important, if you identify them correctly over time, then you don't have to look at all data points, right? So this is the point about active human-like learning that we would like to do. And I think this is possible in the next few years, and I hope that we'll look more into the Bayesian principle to bring this type of thing. Okay, how much time do I have? I have 15 minutes for question. Okay, I'm going to take 2 more minutes and finish this. Okay, so I didn't talk about all of these references, but there are lots of, I have put references for every step that I've done. There's lots of relations to many other methods, black box optimization, its relation to natural gradient variational inference, didn't get to that at all. And there's lots of amazing work, and the initial work by Sato, and I mean, he just passed away 2 years ago, and I think the stuff about expectation parameter, natural parameter, it's been there, we just haven't paid attention to it properly and haven't exploited it. And the references are there, relation to black box VI, so these things are all good. Okay, so the question is, how do we achieve lifelong deep learning? And it looks like that we want to do better posterior approximation, but that really means that we need to compute higher order gradients, and this is going to be hard, right? So what are some of other ways that we can solve this problem? So I'm just gonna end with that, and I read this paper recently actually. It's a really, really beautiful paper, and people don't like free energy principle, it seems like, but I think the ideas are all there. And I think what Carl Friston is actually talking about is, the thing that I liked in the paper is there are 2 things about learning. One is perception. So one thing is like, how do you see the world right now? What kind of person you are, and how do you see things that come your way? But the second thing is, what do you want to see in the world? So you can change your head, you can move around, you can do things differently, you can act in the world, and you can change what you see. And these 2 elements is perhaps all you need to learn everything as you go in your life. So you need to know what you know, and what makes you what you are, and how that makes you see the things that are coming your way. And that's the perception. But the second thing is that if you want to be a different person, you can act in a different way. You can change what you see. You can go to a different place, be a different person, explore a little bit more. And so these 2 things are at interplay. Now, I think that the posterior approximation really connects the 2, right? So models are a representation of the world, but we cannot really pay attention to everything that we have known so far, right? And approximations are basically figuring out what's important in the model right now. So they're a representation, they're further approximation of the model. Okay, so by changing the approximation, we could say, what do we care about in our model that's useful for us to act in the world? And then we can act. Okay, so the approximation helps us to learn the model through action by collecting these data points, and I think that's basically what should happen, right? So the hope is that if you can come up with a way in many applications to fill in the data space, to argue what would have happened if you have chosen something else, if you've done something other way, so going like reasoning or causal inference, but the Bayesian principle really sit in there. It's at the heart of the thing. And it sits inside these principles of exploration, exploitation, and causality. So it does form a core part of it. Okay, so just to close the talk, I've been saying this for almost 8-9 months that I'm going to write this, but it's still not out there. I put a very preliminary version, and this is work with Howard Drew, who has really helped me to put all these things together. So thanks to him. And acknowledgement to amazing people, interns who have gone to do much more amazing things. Actually, they're all in Vancouver, many of them, many members at RICAN, many collaborators around the globe that have helped me to do this. And the papers on this practical deep learning is by these lots of young people here, interns and people from all over the place. And here, and other people from my group, and just it'll end up with people who have actually helped me but didn't end up in the talk. This is my team in Japan, and just wanted to show you this, and I'll end with that. Thank you.
What a fantastic talk. So let's thank the speaker again. So there are 2 microphones on the 2 sides of the aisle. So for people who have questions, please use the microphone to ask the questions. Thank you.
Can we ask a question now?
Yes.
Okay. Very nice. Very nice work. So I'm actually a Bayesian statistician. So I'm here.
Where's the third one? That, and then there's another one somewhere. Okay, I can't find you. Please go.
I'm here, so it's fine.
I'll figure it out.
Okay. So it's quite interesting to see the Bayesian as an optimization problem, and also to see the connection between Bayesian and human learning. So in actually recent Bayesian research, people focus a lot on priors. So how to build the best prior to do prediction for the future. And instead of assuming what learned from the past is entirely translatable to the future, people use like dynamic prior, or called dynamic borrowing, where the parameter learned from past is related with what you're going to predict in the future for the next batch or different problem, but not identical. Do you think that's something probably interesting to enhance the generalizability of the model trained using Bayesian deep learning?
Yes, I definitely agree with you. I think the issue with this prior thing, and I don't really know how to do this, is that for neural network, defining what is simple model, what is a complex model is very hard because it's just a black box, right? So I think if you have architecture that helps you to put in the complexity in a principled way, then that would really help. We don't really know how to put priors on this because the models are not really designed in that way. So that's kind of is the difficulty, but I do agree that this type of things should be useful if we are able to actually define complexity in deep learning. I still can't see you, but I'm sorry.
Right,
oh, I can see you now.
Yeah, I'll find you later.
Thank you.
To chat more. Thank you.
Okay.
Hi there. Thanks for the great talk, and very exciting to this lifelong learning is the trick to viability for this stuff. I have a question with 2 parts for the VOGN optimizer versus Adam. I know it's problem specific, but I'm interested in the difference in speed, like how much slower is the VOGN?
Yeah,
and the second related question is for the multitask, the from versus Adam?
Multitask. Oh, for continual learning, like from. Yeah. Okay. So yeah, this is. I didn't really say anything about this, but on ImageNet, it's twice as slow. On other problems, smaller problems, it's 3 times as slow. And this really depends on like how much Bayesian touch that you want to have. So, you want to average with 1 sample from your distribution, 5 sample, 10 sample. That adds the thing. There is this is not really a complexity issue, this is like an architectural issue. So these details are in the paper, but it's because the way that the code is written that you always compute these average gradients, computing individual gradients different is difficult. And there is actually lots of software being written now, so I think that the gap will reduce. Yeah.
So do you think it's the difference, like Big O, is it a log n type of thing, or
No,
n,
it's
or-
actually the complexity class is the same.
Okay.
It's
good.
just an implementation thing.
Okay, so it's just engineering.
Yes, it is.
Excellent. Thank you very much.
For Fromp, is the same kind of stuff. Okay.
Hi, thanks for the talk. I was wondering how the uncertainty estimates you get from Vogel compare to uncertainty estimates you get from Monte Carlo dropout, and if you can use both together, are there best practices here?
I did have a slide here, but I can't find it right now. But yeah, so it does, actually MC dropout doesn't do that badly. But what we actually see in this out of distribution test is that MC dropout is conservative. So it's conservative on the training data that you've used and the test data that you get. So, for both the entropy is high. And for our method, for the training data, the entropy is lower, so you're more confident. And for out of distribution data, it's a little bit, uncertain. So there's small trade-off. MC dropout still works quite well, but there's no way to kind of change the flexibility, and that was the kind of my point.
And does it make sense to use both at the same time? Have you tested that?
Yes. So I'm gonna say this, and this is not out, but this paper hopefully we'll write it or somebody else will write it. But you could do the Gaussian approximation with the diagonal covariance, and then you can do mixtures on top. So you can use, and this is also a minimal exponential family that fits within the same framework. And when you compute the gradients, it turns out that the gradient of the entropy term just be something like a weight decay term. So it's quite simple, actually. So you can do this. Hopefully somebody will do or will do it at some point.
Cool, thank you.
Okay, hi. Yeah, great talk. And I'm from another area. I think you addressed this question that, practitioners, in addition to convergence, to the accuracy of, Adam, they think about timing. Yes, you address that. But, I think there's another question that if we use different models here, like different ResNets or whatever model, do we, this interesting algorithm that you have, it converges always to the, accuracy of, Adam or SGD, the state-of-the-art, let's say, deep learning algorithm. And also, practitioners may go to multi-processor, multi-GPU scenarios and, do all this, hyperparameter tuning and all the tricks. So, this interesting method, achieves that kind of performance, or, yeah?
So far what we have done, mostly I'll say yes, but it's not, just out of, you change one line and everything works. So there's 2-3 additional parameters to see how much global you want to be. And in the beginning you want it to be very local so that you're doing very similar to Adam. So there's a scheduling parameter that you have to tune. But apart from that, things are kind of fine. And I don't know how this, so even on continual learning, we were able to do this. So I'm actually very confident to say that it should work, because whenever we try things, we don't have to work that hard, This is all done in a matter of 1.5 years, So it's, things are working well, and I hope that it works well. But of course, there's a lot of work to be done.
For sure. Yeah. Awesome.
I'm just wondering whether you see any issues with symmetries or kind of non-identifiability, and whether that might be a reason for
Yes.
the underperformance of variational inference.
That's a really great question. So I should have said this, but there's a lot of issue. So you can actually just write the mean field approximation, and if you start looking into the posterior distribution, some of my interns actually did this work. You can see that the marginals all kind of look alike if you look at the weights, right? So it's the parameterization definitely should be restricted. It'd be something else. But if you look into Adam, then Adam has this diagonal, scale vector, and its every learning rate is different, and that kind of works. So I don't really know, So, but this is really, I think, it's a very good question to, I really don't know. But it's important. Yeah.
Hi.
Yes, I'm looking at you.
So during your talk, you mentioned a couple of times the word information geometry.
Yes.
Maybe on the simplest example of gradient descent, one of the first slides you had.
Yes.
Is it possible to have a
yes.
deeper look on that?
Yes. So the information geometry basically comes in from here. So yeah, thanks for asking. I can actually explain this a little bit more. So gradient with respect to mu is essentially equal to the Fisher information matrix inverse times gradient with respect to lambda. And this Fisher information is the Fisher information of the approximation. So it's very similar to mirror descent algorithm where the geometry is governed by the approximation to the posterior. And it's actually really beautiful, I think.
Hi, I was wondering what your thoughts are on how Bayesian methods can be used to improve the sample complexity of learning, such as in few shots learning problems.
Yeah, that's a very good question. I mean, I think this active selection that we do should play a part, although the active Bayesian deep learning methods do not really show a huge reduction in this right now. So there is definitely a gap. But I do think that there's a way to, you don't want to be too aggressive when you're selecting the data example. You want to do exploration, exploitation, and this has to be mixed with the posterior approximation. And they both interact with each other. So if you have a shitty posterior approximation, then you're going to sort of like be more aggressive or more overconfident, and you'll form some opinion of the world that are not true, right? So I think this is possible, but we have to go beyond the Bayesian principle. We have to think about exploration, exploitation, which is the second layer. So that's.
So the follow-up question is: so right now, as far as I know, most of the few-shot learning, data set is fixed, and it doesn't take into account the fact that we need to actually select the data to, label. So is there any data set that you know of, or are you trying to construct a data set that allow us to take that into account?
Yeah, I do like reinforcement learning problems. They're extremely hard. And so actually most of my group is actually trying to look into RL right now because we think that Bayesian principles would be understood better in that context to see how they fit with this bigger learning problem. Yeah. There are others, talk to me later, maybe I'll think of more.
Due to time limitations, we can take one more question. So more questions, please come forward so that I think MT will be here for discussion for a while.
Hi, thank you for the great talk again. We're interested in our group in some compression of neural networks. And I was wondering if you think that the distributions and the related variances of different parameters in the network can help realize which parameters need to be compressed more or less according to how they...
Yes. We have done some experiments. Actually, it should work. But again, if you're pruning as you're going, then you don't want to be too aggressive. It's really this idea of like how fast you should form opinion of the world. So not everything is in there in Bayesian principle. If you compute the exact posterior distribution, then you're fine. It'll tell you what you should do optimally. But you have an approximation. So you need to design an algorithm that does, works with that and not become too overconfident too quickly. It's the same idea. Thank you. So sorry for not giving opportunity to other people, but I'm here to talk to you if you want.
Okay, let's thank MT again. This concludes the session.